Okay. Had some technical difficulties the last couple minutes just getting the live stream going. I apologize for that. But welcome to the last office hour of the Introduction to Data Science module. Just a reminder, I will continue looking at the message board through November 30th. While you continue working on the mini project assignments, but there will not be any more live office hours after today. This week we'll also, or early next week, we'll also be sending out a post-course survey, as well as some instructions for sort of offboarding from the class. A lot of those instructions will just be things that are also covered in this course conclusion video. And you will have until November 30th to complete the assignments, after which Jupyter Hub will be shut off. So part of the course conclusion video is instructing you on how to continue studying these materials after Jupyter Hub shuts down. After Jupyter Hub shuts down, we will process the grades and be issuing certificates. That will take 1 or 2 weeks. So sometime in early December, if you have earned a certificate, you should receive that from us. We will not be, we will only be contacting people who earned a certificate with instructions on how to access that. So only 2 new questions on the message board since yesterday. As usual, if you have any questions for me live, please share those in the chat. DW4, compare results. Okay, this is another one of those where they are posting a bunch of benchmarks to see if they're on the right course. This is a very high z-score. So as I suggested in this answer that I reference almost every office hour, how to check if you're on the right path to a solution. You should always try and form some kind of expectation of what the right answer should be. Your z-scores are very large. the purpose of calculating z-scores in most contexts is that they relate to probabilities of the normal distribution. Note that a z-score of 2 represents an observation with only 2.5% chance of being observed at random, by random chance. A z-score of 10 represents an observation with only, I need to do a quick calculation here. There we go. 1 minus 10. Probability. With such a small probability that it is within floating point precision of 0. The standard used by elementary particle physicists for statistical significance is a z-score of 5. Your z-scores are much more than 10, which in practice we should essentially never observe. Unless you have made some very incorrect assumptions or a calculation error. So just by knowing a little about z-scores, we can form the expectation that the z-scores should probably not exceed 3 or 4 at the most, and probably will not often exceed 2. Knowing that your current z-scores are too large, you may want to look at places in the calculation, in your calculations, that could potentially lead to large z-scores. For example, perhaps your standard error is too small. Or yeah, it's probably that your standard error is too small. So let me check one thing before I post this solution. Not in that browser, in this browser. Note. The correct solution to the problem does in fact feature z-scores that exceed 4 or even 10. However, this is due to the fact that some of our samples are very small and indeed violate some implicit assumptions made in this calculation. Notably, this z-score calculation assumes that all practices are alike in their prescribing in their prescriptions. This leads into the idea of hypothesis testing. Leads into the idea of hypothesis testing, where we are testing, where we assume something like all practices prescribe roughly 4% opioids, and then sample prescriptions from different practices to test this assumption. If the assumption were true, we would have almost no chance of observing a Z-score of 10. But since some practices specifically treat opioid addictions or rely heavily on painkillers, e.g. for surgery, our assumption that all practices, or our assumed hypothesis that all practices prescribe roughly 4% opioids is wrong. I heard some interesting type of real life problem. Shop has data from checks, date, total sum, etc., and customer ID. I think it's not so difficult to predict total sum of each check, but what if we want to find out customer ID? Suppose there are about 70 customers. Is it possible to implement machine learning multiple key class classification with this large amount of classes? I'm not sure this is a very realistic problem. Why it would be really strange to be trying to predict customer ID, because in most transactions we know who we're selling to. In fact, in the US at least, it's legally required in many cases that you know who you're selling to, because by federal law, there are certain individuals and certain states that American businesses may not do business with. So it doesn't seem very realistic to me that you would ever be in a situation where you don't know who you're selling to and would need to, for some reason, predict customer ID. That said, you've asked sort of a more you're asking a sort of more general question that you identified, which is, how can we do a multi-class classification with a large number of classes? So in some sense, you can think of regression as being sort of a similar problem. They're not quite the same, because regression, mathematical differences between labels must have meaning. But in the case of having many qualitative differences, I would say it's not unusual that if you have many qualitative categories, you can start to make some approximation of a quantitative, what a meaningful quantitative difference between those qualitative categories might be. You know, philosophically, something that many people wonder in different contexts is like, at what point does a difference in degree become a difference in kind? Meaning, at which point does a quantitative difference become a qualitative difference? And there is, I think, this question expresses a certain degree of like ambiguity where it may be possible to encode qualitative differences quantitatively in a way that's maybe arbitrary but not totally meaningless. So that's one approach, trying to turn a large multi-class classification problem into a regression problem. The other thing is, if you have a very large multi-class classification problem, simply trying to break it up into smaller problems. It's, for instance, say you were trying to predict where, say you're a travel agency and you're trying to predict where people might want to travel to, where a given, like, you have a customer's history of purchases and where they're from and other data on them, how old they are, do they have children, that sort of thing. And you're trying to predict where they might want to travel to next. Well, if you are doing it by city, then you have a classification problem involving millions, potentially, of target labels. If you're doing it by country, you have, hundreds of target labels. If you're doing it by region of the world, you're maybe talking about several dozen, something under 100. And if you're talking about continents, you're talking about 7 target labels. So you can also try and reduce the granularity of the problem, which is sort of equivalent to like breaking it into smaller problems. You say like, okay, if I'm interested in what country they might want to go to, then I'm going to break this up into smaller problems where I'll predict that later. But first, I'm just simply going to try and predict continent. And then once I have predicted continent, for those continent groups, I will build separate models that predict country. So you can try and sort of telescope the problem into different pieces where you reduce or increase the granularity at different steps. Those aren't necessarily built into scikit-learn in any kind of way. Neither approach is built into scikit-learn, and you would need to come up with your own framework for those sorts of approaches. I have not heard of these terms, association rule learning or a priori algorithm. I don't know if they are related to neural networks. What I have heard of collaborative filtering, which is often used in recommendation engines, where you look for customers essentially with similar profiles to the customer you are trying to predict, and use those customers' purchasing preferences as a way to recommend products to the customer for whom you are trying to advertise to. This is like when on many online stores or news sites, it says like other customers viewed these products, or other people who read this article are interested in these other articles. Those are using what's called collaborative filtering. I don't know if maybe that's related to this association rule learning term, which I've never heard of. So just reading this like quick summary in Wikipedia, this is really vague, and I can imagine a lot of implementations that sort of meet this definition. So I would probably have to dig more into maybe what the exact mathematics of the process they use for association rule learning is. But association rule learning, according to kind of the very brief definition here at the top of the Wikipedia article, sounds similar to, or sounds more like a high level concept rather than a specific algorithm. Yeah, I would have to read more about this. It looks like there's some set theoretic mathematics that I would have to think about in order really to comment on this approach. But it's not related. I mean, looking at that, I can say at least that it's not related to collaborative filtering. So someone struggling with PW question 4. It appears there you're selecting the single prescription with the highest items prescribed in a postcode. The question asks that we compute the total items prescribed for each postcode BNF name pair, and then select the highest total from each postcode. Therefore, when constructing total items by post, you won't, and rather than using only postcode as your key, you'll want to use postcode BNF name, i.e., instead of grouping by postcode, postal code, you first need to group by both postal code and BNF name, so that you can compute the item totals for each BNF name in each postal code. A full overview of the approach to this question can be found in this previous answer. Okay, that's both of the questions on the discussion board. Of course, I will be here until the end of the office hour. We have 22 minutes left. So any additional questions you have, I'd be happy to answer them. When will we start the new course about machine learning? That will be happening in January. I don't know the exact date off the top of my head, but yeah, that'll be happening in January. We'll be in touch with everyone who completes this course. I believe the first run of the machine learning course is going to be open only to those who completed this course. Subsequent iterations of that course may be opened up more broadly. But currently, I think it's just going to be for people who completed this course. When do we use grid search in scikit-learn? Grid search is principally used for hyperparameter optimization. For instance, if you're working with a decision tree or a random forest, when you're trying to optimize like the number of samples that you need at a minimum to create a leaf or a split point, or if you are optimizing the depth of those trees, or if you are trying to optimize a regularization parameter for logistic regression or ridge regression or something like that, that's when you usually use grid search. Grid search is not the only method of hyperparameter optimization. There's also random search, which I believe scikit-learn also has, randomized search CV. So this is similar to grid search, except instead of trying out hyperparameters along predefined grid steps, it will randomly pick out points in the space of hyperparameters that you define according to probability distributions over that space that you define as well, which can be useful. Part of the difficulties of doing a grid search is that for each hyperparameter, your number of grid points grows exponentially. In other words, as you add more dimensions to a space, the size of that space grows exponentially fast. One way to see that is like if you think about going from a line, one-dimensional, to a square, two-dimensional, to a cube, three-dimensional. The number of points you need to define those objects is a line takes 2, a square takes 4, and a cube takes 8. So it's growing exponentially fast as you go up in dimensions. Random search rather than grid search, we're not going to hit every grid point. And that's helpful for 2 reasons. One, it gives us a easy way to define how many iterations we can afford to spend in terms of time for doing our hyperparameter search compared to grid search, where if we want to define the number of iterations we're going to use, then we need to essentially encode that in the number of grid points that we specify. Secondly, a grid search is sort of a uniform probability search over the space of hyperparameters. Whereas with a randomized search, we can encode some prior beliefs that we might have about what the correct hyperparameter value should be, where maybe we think the regularization parameter should be around 0.1, but maybe not exactly 0.1. And we're pretty sure it shouldn't be 1 or 0.001, but we're not sure of the exact value. Well, we can allow the search to extend to any value, but we can have the probability distribution taper off as it gets further from 0.1. So the possibility that we spend time searching values far away from 0.1 is relatively small, while the probability that we search around 0.1 is pretty high. So randomized search in many ways tends to be better than grid search, but it's also a little bit more, grid search is a lot more intuitive. And so we teach that first, since this is an introductory course, and we want to make sure you understand the idea of hyperparameter search before, or optimization, before we move on to more advanced methods. Yes, the machine learning course is an incentive to finish this course. That's true. I just tried to use KNN for multi-class classification and find out if we use labels which are not consecutively, then we predict labels which is not in our origin label space. I didn't know that was the case. I don't know why you would need non-consecutive labels. I also don't know why scikit-learn would predict a label that's not in the original label space. You know, one thing to do when you find a peculiarity like this and you think it shouldn't work that way is you can go to the scikit-learn GitHub. You can go to issues and you can open a new issue. Now, if you're going to do that, I do suggest that you do a good job of it. You should have a descriptive, just like for the message board, you know, we should have a descriptive title. We should give a good description of what we're trying to do with an example and code, and explain exactly what we think is wrong and the way we think this thing should work. But yeah, I wasn't aware of that. That said, I would expect in most cases that you would have have consecutive labels. And furthermore, you might want to be careful that you're using a k-nearest neighbors classifier and not a k-nearest neighbors regressor, right? Because for a regressor, this would be very normal behavior. We expect regressors to predict numbers that lie in between the various labels that we supplied them. Okay, yeah, sometimes it's just a mistake. That's all right. Yeah, you're very welcome. I'm glad that so many of you have found this helpful, and glad to see so many uh, returning participants in the office hours week after week. And I look forward to hopefully seeing many of you again in the next course. By the way, incidentally, so since I said like, hopefully I'll see many of you again in the next course, I am not entirely sure that I will be teaching that course. It may be a different instructor, but we have many talented instructors on staff. So whoever you end up with, I'm sure will be, you know, very capable and very helpful. It might be me. It might be someone else. Okay. Well, that brings us to the end of the office hour. So I'm going to sign off. And as mentioned, I'll continue to be active on the message board. But thank you again. And I hope you all have a good rest of your day.